In this follow along, we'll look at the oxidation of an alcohol using Jones reagent. Now, what's important to remember about Jones reagent is that this is a chromium-based reagent. And so, trying to avoid chromium is one of the things that chemists would like to do, because chromium is toxic and you have to waste it at the end of the day. And so the fact that this reagent requires chromic acid is what makes it pretty harsh. If ever you see a synthesis using Jones reagent, they tend to be on simpler and less functionalized systems because it is chromic acid. It's a very harsh condition to use. Also, if you are dealing with a primary alcohol, you're going to oxidize all the way up to the carboxylic acid because it's very difficult to stop the oxidizing train that is chromic acid. So oftentimes Jones reagent is used to convert secondary alcohols to ketones in simple systems, and sometimes to go all the way to the carboxylic acid. But there are other options out there for primary alcohols to go to the carboxylic acid. Let's review the mechanism for a Jones reagent so that we can understand the flow mechanistically, because we're going to see a general trend for oxidation. Let's start with a very simple primary alcohol. Now, chromic acid, I'll draw this up above. Looks like sulfuric acid, but with chromium in the middle instead of a sulfur. Now, effectively, the mechanism that we're going to see, the sequence of mechanisms, is first we're going to replace this hydrogen with the chromium. Now, I always introduce this as an SN2 because chromium has d orbitals. And so it's not a carbon. We don't have to go in, up, down, out. With phosphorus and sulfur and the transition metals, we can get away with protonating one of the oxygens and then simply doing an SN2. Why? Well, because it's got d orbitals. There's no evidence to support the fact that one of the oxygens becomes negative in the chromate species. We can simply just exchange. So let's just do an SN2 here. What I have now, I'm in aqueous media, aqueous acidic media. So remember, we're in high acid and we've got lots of water. That's what the conditions are when you're using Jones reagent. Okay, so we could say, all right, the water deprotonates. You're just generating more acid here anyway. Acid-base chemistry, the electrons go into the oxygen. I am now here. Okay. What I have done from start to finish is I have exchanged a hydrogen for the chromium. In this SN2 exchange, that's effectively what I've done. The oxygen is the nucleophile and it attacks the chromium in an SN2 style, and then the proton is removed through acid-base chemistry. And I form this chromate ester. Okay? Now what happens? Well, now we're going to do an E2 process, and you can think about it very similar to a regular E2, because what happens as a result of an elimination? You get a new pi bond, right? So what's going to happen is the water is going to act as our base, and it's going to grab the hydrogen on the carbon next door. These electrons are going to become the new pi bond. And look what happens. The the chromium gains the electrons. Chromium gains electrons. It is getting reduced. So the chromium is getting reduced. It gains the electrons. As the oxygen-carbon bond gets a new pi system, remember in organic chemistry, we define oxidation as a carbon losing hydrogen bonds and gaining more oxygen bonds. And that's so our organic molecule is becoming oxidized as the chromium is getting reduced. Redox chemistry. You can't have one without the other. You can't oxidize something without reducing something else. So the chromium is getting reduced as our organic compound is getting oxidized. So this was the E2 mechanism right here that we saw. If I wanted to define it, that's what it would be. All right, so now remember, there's another hydrogen there. I have an aldehyde. But things don't stop. I'm under acidic aqueous conditions. That's important. This is what's going to drive the reaction forward. So under these conditions, I can't stop the train that is these harsh conditions. So the carbonyl gets protonated under these conditions. And the water is going to be my nucleophile. We saw this in the ketone aldehyde chapter back in Orgo 2. We form a hydrate. Now, hydrates are not stable, but they exist. We know that they happen. They're just not, you just don't isolate them. So this is a hydrate, and we know that those are not stable. So this is an equilibrium, and we know that it favors the carbonyl over the hydrate, but the hydrate nonetheless is formed. Now what's really interesting about this is that if the hydrate forms and we still have the chromium, the Jones reagent around, notice that we have another alcohol. Like the hydrate has two alcohols on it. So in that hydrate form, it's reactive with another chromium species. So we're just going to repeat the SN2E2 again. So what we've done here is a acid catalyzed 1,2 addition, right? Which generates a little bit of hydrate, and that hydrate can react with another chromic acid. So it's the presence of the water and acid that allow this reaction to continue from the aldehyde because it generates a hydrate in situ. So pick an alcohol. I'll just pick this bottom one. It's going to do our SN2. Let's protonate to make it a good leaving group under acidic conditions. And we're doing exactly what we saw before. SN2 again. I've got my chromium. I've deprotonated the extra hydrogen using water, right? Water is probably coming around again and taking off the extra proton. It's just going in an acid-base equilibrium, right? H2O becomes H3O plus, right? Which is a hydronium ion, which is just acid and water. We've done the SN2. Now we're going to do the E2. We're going to use water again as our base. Again, under highly acidic conditions, our bases are not very strong, but that's all we need is to take off that extra proton. Take those 2 electrons, dump them in to make our new carbon-oxygen bond. Reduce the chromium by having it gain electrons. Here is our E2. And there we are. We made a carboxylic acid.